Hello students, welcome to Sri Jayendra's Ring Zone classes. I'm your friend and mentor for coming classes with respect to physics. This is lecture number 6 of a unit Mechanical Properties of Fluids. So let's begin with today's class. In today's session we are going to discuss about the first of viscosity. Let's have a look what viscosity is. Let's suppose we have a two flask, and in this two flask we have equal amount of water and oil in this two similar flux. So if we observe them, that in one of the flask we have filled with the water, in another flask we have filled the oil, it is observed that the water flows out of the funnel very quickly, while other end oil is found to flow down very slowly. So there are certain property in this two, or there would be a certain difference between the properties of this two, due to which one of the fluid is moving down very easily, while one of the fluid will take a certain amount of time to get it down. What it is? Let's have a look. It's a viscosity. It is the property of fluid by virtue of which it opposes the relative motion between its layers is called as a viscosity. So what we have given is that this is the flow of the liquid from here to here. There is a flow of liquid, and let's suppose we have divided this layers into certain segments. That let's suppose this is first layer, this is second layer, this is third layer, this is fourth, and onwards. So there is an opposition to the relative motion between the adjacent layers, and this layers will oppose the relative motion between each objects, and that's why there is a certain friction kind of thing is happen. Let's have a look. So if you see this situation, there is the tangential force x on the adjacent layers of the fluid, which opposes the relative motion between the layers of the liquids, or even same thing can happen with the gas. This force is called as the viscous force, or we can say this, that this is the viscous drag. That you can see this, if I pull this from this, then there is a force of opposition in the opposite direction. Let's look at the velocity gradient. So suppose this is the layer at the bottom is the stationary layer, and all the layers starting from the top, it's a let's call it first, second, third, fourth. So starting from the top, they are moving in the positive x direction. So this the rate of change of velocity with distance measured from the stationary layer is called as the velocity gradient. Basically it's a dv by dx. So as you can see this, if you observe the motion of any of the layers, if you observe the motion of the any of the layers, that let's suppose this layer is moving in the forward direction, then this layer will slide it in the negative x direction. If this layer is moving in the forward direction, then the third layer will apply a resistive force in the negative x direction, and so on. So this is what a viscous force is. I hope this is clear. So let's suppose this is the situation, that this is a plate in which a different layers of fluid is there, and let's suppose this plate is at rest while this is being applied with certain force F. So now let's suppose we divide this layers into different names. It's a first, second, third, and fourth layer. So after some times, if you see this situation would be something look like this, that this is at rest while this is in motion, something like this. I hope this is clear. Yes, this is the topmost layer on which force has been acting. It's a first, second, third, and fourth, something like this. So again it is at rest, and if I say that this layer is having velocity v1, this layer is having velocity v2, this layer is having velocity v3, and this layer is at velocity v4. So as I understand that v4 is at rest, it's a v4 is equals to 0. v1 is having the highest velocity. v1 is having the highest velocity because it is moving in the positive x direction. So we can understood that v1 is greater than v2, is greater than v3, is greater than v4, as I understood that ideally v4 should be at rest. I hope this is clear. Is it clear? Is it clear? Now let's suppose consider this one of the different situations in which, let's suppose this is a pipe, and this pipe, let's suppose a certain fluid is flowing like this. If I take a cross-sectional vision, if I take the cross-sectional vision of this, then I can have this kind of mechanism that, let's suppose this is first, second, let me redraw this. There are certain layers. Yes, it's a first, it's a second, it's a third, it's a fourth. So as this layer is in contact with the wall of the pipe, this layer is in the contact of the wall of the pipe. So this is at rest, this is at rest, having ideally having a zero velocity. It's a v4 is equals to 0, v1 equals to 0, and approximately v2 equals to v3. They both have a linear velocity. That means if you observe the pipe, or if you observe the water that has been flowing through the pipe, then you might observe that all the water layers that are in contact with the pipe, it is at rest, while the other layers, that is the central region passes through that pipe very easily. I hope this is clear. Now let's discuss the certain terms about the velocity gradient as well. It's a rate of change of velocity with distance measured from stationary layer is called as the velocity gradient. And velocity gradient could be written as, it's a dv by dx. It's a, if I take a unit of it, velocity, it's a meter per second, x, it's a 1 by meter. So this meter has gone, and only the term that has been left, it's a 1 by second, so that is per second. So a dimension of velocity gradient, it's an m0 l0 t to the power minus 1. This is velocity gradient. I hope this is clear. Is it clear? Is it? Are you sure? Great. So let's check it out. Certain quick questions. First, the property of fluid by virtue of which it opposes the relative motion between its layer. Yes, this is what we call as a viscosity. Next, the streamlined flow of a fluid is enough to a turbulent flow is if velocity is greater than, yes, if it is beyond critical velocity, then it will convert itself to the turbulent flow. Next, hurricane. Yes, hurricane is an example of turbulent flow. All the irregular flows are came into the category of the turbulent flows. Next, the rate of change of velocity with distance measured from static layer. Yes, it's a rate of change of velocity with respect to distance. It's a velocity gradient. This is dv by dx. I hope this is clear. Is it clear? Is it? Are you sure? Do you have any doubts? Is there anything? Is there anything? Are you sure? Great. So let's now discuss a two very important law. They are the Newton's law and Stokes law. So this is the viscosity that we have discussed. It's a property of fluid by virtue of which it opposes the relative motion between its layer. This is called a viscosity, and we have already discussed that they are going to provide a repulsive kind of force, or we can say a force in the opposite direction, so that they does not glide from one surface to another. Now let's consider a liquid flowing over a horizontal surface. and each slower moving layer of the liquid exerts a tangential retarding force. When I say retarding force, that means you understand this, that it will act in the opposite direction on an adjacent faster moving layers, and the value of the viscous force is given by the Newton's law of viscosity. So what Newton's law is, let's have a look. He said that for a streamlined flow, viscous force acting on any layer, for any streamlined flow, viscous force acting on any layer is directly proportional to the first area of the layer, and second it depends on the velocity gradient. So it basically depends on the two terms. It's a first, it's a force that is directly proportional to the area, and second it depends on the velocity gradient. While I say velocity gradient, it's a dv by dx. So if I remove this proportionality symbol, this is equals to F is equals to eta into A into dv by dx. Now what is this n? What it is? This is coefficient. This is coefficient of viscosity. I hope this is clear. So let's discuss what coefficient of viscosity is. We have this relation from Newton's law. It's an F is equals to eta into A into dv by dx. It's a velocity gradient. So numerically if A is equals to 1 and dv by dx equals to 1, then its a coefficient of viscosity is equals to the force, and its a relation between SI and CGS unit of eta. So SI unit, it's a 1 Newton into second per meter square, and that would be equals to 10 poise. So this is what we call as a poiseuille. SI unit of SI unit of coefficient of viscosity, it's a poiseuille. It's a poiseuille, yes. And CGS unit of coefficient of viscosity, it's a dyne per into second per centimeter square, or even that has been called as a poise. So it's a SI and CGS unit. It's a 1 poiseuille is equals to 10 poise. Dimensions are dimensions of the coefficient of viscosity. It's an m1 l minus 1 t minus 1. And eta, this coefficient of viscosity depends upon the nature of the fluid. So it is a materialistic property. It vary between material to material. I hope this is clear. Is it clear? Is it clear? Are you sure? Great. So have you noted this? It's an F is equals to eta into A into dv by dx. If not, please note it down. Please note this. Have you did it? Have you? Great. Now let's work for the questions. So the question says that a boat of area, a boat of area 10 meters square floating on the surface of a river, floating on the surface of a river is made to move horizontally with speed of with speed of 2 meter per second by applying a tangential force. If the river is if the river is 1 meter deep, the river is 1 meter deep, and water is in contact with the bed is stationary. find out. Find viscous force acting. How will you do this? How will you do this? They have given a viscosity of water that is equals to 0.01 poise. This is given. So what all they have given is that a boat of area, that is the area is given, it's a 10 meter square, is floating on the surface of a river, is made to move horizontally with speed of 2 meter per second. It's a upper layer. By applying a tangential force, if the river is 1 meter deep, it's let's say x, which is 1 meter deep, and water is in contact with the bed, which is stationary. That means change in velocity, it's a 2 minus 0, which is equals to 2 meter per second. And I need to find out the viscous force acting. So this is equals to F is equals to eta into A into dV by dx. This eta, this eta, that would be equals to sorry, this is equals to 10 to the power minus of 2 into 10 to the power minus of 1 multiplied by it's a dV by dx. So this is equals to 10 into 2. So if I find it out, it's this is equals to 0.02 Newton. I hope this is clear. Is it clear? Is it clear? Are you sure? Are you? Great. So ready for one more question? Are you ready for one more question? Let's have a look. Suppose the question says that velocity of water. So velocity of water in a river is 18 kilometer per hour at the surface. If the river is 5 meter deep, find the shearing stress between the horizontal layers of water, and viscosity of water is 10 to the power minus 3 poisuli. It's a pi. So what is given? He has given that velocity of water in river, it's an 18 kilometer per hour. So when I write it's an 18 kilometer per hour, and if the river is 5 meter deep, okay, so 18 kilometer per hour, it's an 18 into 10 to the power 3 divided by 60 into 60 divide by, and this is 1 by 5 meter dip, this is equals to dV by dx. So, and even the coefficient of viscosity has given, it's a 10 to the power minus of 3 poisuli. So this F is equals to, it's an eta into A into dV by dx, and this is what they ask a shearing stress. That means F by A is the requirement, so it's a eta into dV by dx. It's an eta that is equals to 10 to the power minus of 3 multiplied by this is 0, this is 0, and this 3 zeros are there. You can remove the 2 and the rest of the 2 will remain. So this is again 6 threes are, and this is 3 twos are, this is 2 fives are, and 5 has been removed. So this is F by A. It's a 10 to the power 3 minus of 1. This is equals to 10 to the power of minus 3 Newton per meter square. This is the shearing stress. I hope this is clear. This is shearing stress. Have you got this? Now, do you have any doubts over this? Is there anything? Is it clear? Is it? Are you sure? Are you sure? Do you have any doubts? Is there anything? No? Great. Now let's look at the different law. Second law, it would be the Stokes law. He said that the viscous force acting on a small sphere falling through a medium is directly proportional to the radius r of the sphere, its velocity v through the fluid, and coefficient of viscosity of the fluid. So basically it depends on the three terms. It depends on the eta, which is coefficient of viscosity. It depends on the r, it is the radius of the sphere, and depends on the velocity v with which it is traveling. So from this, if I remove the proportionality symbol and if I add certain constant, it's a 6 pi, which is equals to F is equals to 6 pi eta r into v. This is the Stokes law. And this viscous force is velocity dependent. Look at the dependency of this. It's a dependency, it's eta. It depends on dependency is the radius of an object, as well as it depends on the velocity of an object. This is equals to F is equals to 6 pi into eta into r into v. It is same as the somehow friction force, but it is just like a friction force. It is not exactly as a friction force. If I compare this Stokes law, if I if we compare this Stokes law and friction force, then this force Stokes law depends on the size of an object. This depends on the size of an object. Friction does not depend. Friction does not depend on the size of an object. The Stokes law depends on the velocity of an object. This force of friction, force of friction does not depend on the velocity, or yes, does not depend on the velocity of an object. Yes, this are biggest differentiation between these two, that whatever could be the speed of friction would be the same, but here as soon as speed is increasing, Stokes law will started increasing. I hope this is clear. Yes, great. Now I hope this is clear. Great. Now let's discuss a terminal velocity, and let's derive a formula for the terminal velocity. So first let's understood what terminal velocity is. We see that when a spherical body falls through a viscous fluid, it experiences a viscous force, and the motion of body is initially accelerated, and its velocity begins to increases. At certain time, this spherical body attains a constant velocity, and that velocity is known as the terminal velocity. So when body attains terminal velocity, when body attains terminal velocity, net force acting on a body is zero. So no net force is acting on the system, on the object, when it has achieved the terminal velocity. So let's look at this. It is the spherical body, and it is going to be dropped into this viscous fluid. So when it has been traveling through this sphere, let's suppose something like this, then it is having a certain forces which does exist. One of the force is the m into g, it's a weight force. Another force is the fb, it's a force of buoyancy. And one more force, it's a force due to drag force, it's a Stokes law, it's an f is equals to 6 pi eta av. So when this total upward force is equals to the mg, it is going to attain a terminal velocity. I hope this is clear. So basically it's a total downward force equals to the weight of the sphere. The weight of the sphere could be written as it's of m into g, and this mass could be replaced by the volume into density into g. It's a 4 by 3 pi r cube into density into g. So now this is the downward force, which is the mg, and the total upward force, this total upward force can be calculated as viscous force plus upthrust due to the medium. Now viscous force, it's a 6 pi eta into a into v, and the upthrust due to the medium, it's a 4 by 3 pi r cube into density into g. So total downward force, it's this 4 by 3 pi r cube into density of solid, and this is density of liquid. So it's a total downward force is equals to total upward force, which is something like this. It's a 4 by 3 pi r cube, it's a density into g, that is equals to 6 pi eta rv plus 4 by 3 pi r cube density of liquid into g. If I solve this, what I am having is this much. It's a v is equals to 2 by 9, v is equals to 2 by 9 into pi r square multiplied by density of solid minus of density of liquid into g divided by eta. So this relation, this is velocity, is what we call as the terminal velocity of an object. It is something like this v is equals to 2 by 9 pi r square into density of solid minus density of liquid divided by eta into g. This is terminal velocity. Look at its variations. This velocity v could be changed by changing this radius. This could be changed due to density of solid minus density of liquid. This could be changed due to effect in gravity. Even this could change with change in the fluid, because it depends on the eta as well. So this all are the variations. This all are the variations that can be achieved by this. I hope this is clear. Is it clear? So please note this down. Please note this, and and once you noted it, we will switch to the questions. But before we switch to the questions, if someone asks me that plot a graph for velocity versus time in which object is going to attain a terminal velocity, how it would be? So initially it has started from the zero, and it will keep on increasing, and at certain stage it will be at constant velocity, and this constant velocity is very close to the terminal velocity. It is something like this. This is the graph of the particle who has been just released, and after some time it is going to achieve the terminal velocity. I hope this is clear. Is it clear? So please keep this in mind. Depends on the square of the radius, depends on the density of solid minus density of the liquid, depends on the g, depends on the 1 by eta. Have you noted it? Have you? Great. Let's work for the question. Suppose if 1000 drops of a liquid traveling with terminal velocity of 10 meter per second combines to form a bigger drop. Find out terminal velocity. Find out terminal velocity of a bigger drop. How could you get it? What is? What do you think? What can be done? So what we understand is there are 1,000 drops are there, and this 1,000 drops are traveling with a terminal velocity of 10 meter per second, and this all drops combine to form a bigger drop. So when they combine to form a bigger drop, their volume will be conserved. So volume will be conserved, and when I say volume will be conserved, I mean that n number of drops each having the volume of 4 by 3 pi r cube would be equals to a bigger drop. It's a 4 by 3 pi into r cube. So this is the radius of the smaller drops, and this is the radius of the bigger drops. So this 4 by 3 pi could be gone, and this is equals to n into r cube, which is equals to r cube. From this, it's a n to the power 1/3 into r is equals to r. From this, if I square on both the sides, it's a n to the power 2/3 into r square, that is equals to r square. I hope this is clear. Is it clear? Is it clear? Now, it's a terminal velocity of smaller drops. It's a 10 meter per second. I need to find out the terminal velocity of the bigger drops. So if I take a ratio, of this two, it's a Vt2 divided by Vt1. This is equals to a 2 would be the newer drop and 1 would be the older drops. This is equals to r square divided by r square. So when I say it's an r square divided by r square, this r square would be equals to n to the power 2/3 into r square divided by r square, and this 2 has been cancelled out. This is Vt2 divided by Vt1. So this is Vt2 that we don't know. Vt1, it's a 10 meter per second. This is equals to n to the power 2/3, and it is 1,000 in my case. So this is equals to 1,000 to the power 2/3. So this is 1,000 to the power 1/3. It's a 10 to the square. It's a 100 into 10 would be equals to Vt2, which is equals to 1000. It's 1,000 meter square per second. This is the velocity. This is the velocity, or I should say terminal velocity of bigger drop. I hope this is clear. Is it clear? Is it? Are you sure? Now, do you have any doubts? Is there anything? Is there anything? Is it? No? Great. Ready for the next question? Let's have a look. Suppose that this is the container and it has been filled with the fluid. So let's suppose one of the object is there, and this is at height h. So the question is, find out height h if find out height h if after falling a distance h from rest, particle is having constant velocity. So think over this and let me know what could be done. What do you think for this? They said that find out height h if an object is falling for a distance h from rest. So he it is going to be released from rest from here. Particle is having constant velocity. What does it mean? Constant velocity. When they said it's a constant velocity, that means it attains a terminal velocity. Yes, indirectly. They are saying that this object is going to attain a terminal velocity after traveling for the distance of h. So what I understood is this is v square is equals to u square plus 2gh. From this it's a u equals to 0 because it is going to be released from rest, and this is equals to 2gh. This is equals to v square. From this it's a v which is equals to root of 2gh. Now it's a v which is equals to root of 2gh, which is equals to terminal velocity, which is 2 by 9 a square by eta into bracket density of solid minus density of liquid divided by g. So this is the situation where it's a 2 into g into h. This is equals to 2 by 9, which is equals to 4 by 81 into a to the power 4 divided by eta square into density of solid minus density of liquid whole square divided by g square. From this h can be derived very easily. I hope this is clear. Is it clear? Is it clear? Is it? Are you sure? Are you? Great. So now do you have any doubts up till now? Is there anything? No? Let's look at the quick questions. The question says that viscous force per unit velocity gradient is also called as, it's a viscous force per unit area per unit velocity gradient, it's a dv by dx. Yes, this is eta, it's a coefficient of viscosity. Next, if viscous force F is equals to 10 Newton and velocity gradient, it's a dv by dx which is equals to 10 1 by second, it's a second inverse. Okay, then what is the area of liquid layer? So this is F is equals to eta into a into dv by dx. This force is 10 Newton, coefficient of viscosity it's a zero point 0.1 multiplied by area, that is what we are looking for, it's a 10. So it's an area which is equals to 1 by zero point 0.1, it's a 1 by 10 which is equals to 10 meter square. This would be the answer. I hope this is clear. Is it clear? So do you have any doubts? Is there anything? Is there? No? Great. Now let's look at the Reynolds number, what it is. So flow of liquid inside a tube remains a streamline if its velocity is less than a critical value. But if velocity is greater than the critical value, then laminar flow converts into the turbulent one. So it is basically a critical value, basically it's a critical velocity which determines that whether this flow is a streamline one or whether this flow is the turbulent one. Now, what is critical velocity? The critical velocity is directly proportional to the eta divided by density into the diameter of a tube. It's a eta divided by rho into d, and where d is the diameter of the tube, eta it's a coefficient of viscosity of the tube, and rho it's a density of the liquid through which liquid is it's a density of liquid. I'm sorry. I hope this is clear. Is it clear? So from this we have derived one number, that is what we call as the Reynolds number, and this Reynolds number could be given as it's a n, that is what we call as a Reynolds number, that is equals to, it's a rho into v into d by n. It's generally, or sometimes it has been denoted as, it's a density into velocity into diameter divided by n. So it's a pure number. This is a pure number, and this number does not have any units or dimensions. So again the question remains as it is, that how could I understood that whether this flow belongs to a terminal one or streamline one. I hope you understand the question. So by certain experiment, Reynolds has given this, that if Reynolds number lies between 0 to 2000, then the flow of the liquid is laminar, or I should say streamline. It's a streamline or laminar, whatever you call it. If Reynolds number lies between 2000 to 3000, 2000 to 3000, then this laminar flow may change to the turbulent flow. And if eta, its Reynolds number, is greater than 3000, then the flow of liquid is turbulent. Basically this range, it is the range of 2000 to 3000. It's basically a case of the unsteady rate. It's an unsteady rate. Unsteady means if this flow is less than 2000, it will move to the streamline. If this flow is greater than 3000, it will move to the turbulent. So basically it will switch over from one layer to another, from one phase to another phase. But if it is less than 2000, it is streamline. If it is greater than 3000, it is turbulent, that is for sure. And from 2000 to 3000, from 2000 to 3000, it is going to switch over. I hope this is clear. Is it clear? Is it? Great. So if Reynolds number lies between 0 to 2000, then the flow of the liquid 0 to 2000, it's a laminar or streamline flow. If they have been asked that if n lies greater than, if n is greater than 3000, then it would be, yes, then it would be the turbulent one. I hope this is clear. Next question. The constant velocity, the constant velocity with which a spherical body falls through the viscous fluid, it's, yes, it's a constant velocity, is this velocity is known as the critical velocity. Next, if velocity is greater than the blank, laminar flow converts into turbulent. Yes, if velocity is greater than the critical velocity, then laminar will convert to the turbulent. And if Reynolds number is greater than 3000, if Reynolds number is greater than 3000, then the flow of the liquid is considered as the turbulent. So basically you need to remember this ranges, that if my Reynolds number lie between this range, it belongs to streamline. If this number lies between this range, this will be the streamline, this will be the turbulent, and so on. I hope you understand this. Have you got this? Have you? Do you understand this? Is it clear? Is it clear? Great. So let's have one numerical based on this. The question says that it's a water is flowing. Water is flowing in a pipe of in a pipe of radius 1.5 centimeter with with an average velocity of with an average velocity of 15 centimeter per second. What is the what is the nature of flow? This is the question. So to find out the nature of the flow, that means they want to identify that whether it belongs to the turbulent flow or whether this belongs to the streamline flow. So what all is given, this turbulent or streamline could be decided by Reynolds number, and that could be given as it's a rho v t by eta. So let's check it out what all has been given. They said water is flowing in a pipe of radius 1.5 centimeter. This R, its a radius is given, it's a 1.5. Convert this to a meter, it's a 1.5 into 10 to the power minus of 2 meter. And as they have given the radius, what I want the diameter. It's 3 into 10 to the power minus of 2 meter. Next, they have given the velocity, it's a 15 centimeter per second. So this is again 15 into 10 to the power minus 2 meter per second. What next? Great. So now let's find it out, the RE. It's rho into V into D divided by eta. So they said the water is flowing. When they said water is flowing, it's a 10 to the power 3 multiplied by velocity. It's a 15 into 10 to the power minus of 2 multiplied by diameter of the pipe. This is 3 into 10 to the power minus of 2 divided by eta. It's again 10 to the power minus of 3. If I solve this, if I solve this, this will belongs to a 4500. Yes, and as this is 4500, which is greater than 3000, so this flow is turbulent. So you need to simply calculate this and give the conclusion that this flow belongs to this region, this flow belongs to this region. That's it, you did it, great job. I hope this is clear. Is it clear? Is it? Are you sure? Great. So let's wind up this session over here. We in this session we have discussed a very small but number of concepts. We have started our discussion with the velocity gradient, then we have switched to the Newton's laws, then we have switched to the Stokes law, and at last terminal velocity and Reynolds number. Please go through this all are the smaller topics, but they have an ability to give the questions. Basically, if you see the previous year asked questions, you will find many questions from the terminal velocity as well as many questions from the Stokes law. So please go through this, please revise it, have a questions based on this, and this will make our task much easier if we have revised it thoroughly. Thank you, have a good day, take care, bye bye.